somewhere between a pine tree and the Parthenon. Neri Oxman's vision for the future of cities. Architects, urban designers, and developers often refer to the built environment, a term of art intended to explain all the buildings and places that make up our urban world. The environment part of that term, though, rarely refers to the actual environment, otherwise known as nature. Buildings, from the highly carbon-intensive concrete in their foundations to the excessive energy needed to create and run a skyscraper, don't tend to operate in harmony with the natural world. Until recently, Oxman led the mediated matter group at the Massachusetts Institute of Technology. She continues to explore the intersection of biology, materials science, and architecture through her firm Oxman Architects, founded in 2020. These ideas are the subject of a new solo exhibition at San Francisco's Museum of Modern Art, running Saturday through May 15. The show features 40 works of art dating back to 2007, including seashell-based pavilions designed to decompose, and masks that capture and visualize a person's final breath. Here, Oxman tells Fast Company about how biological materials and emerging fabrication technologies can inject more nature into the built environment. Fast Company. Architects and builders are increasingly concerned with green building, reducing the embodied carbon of a project or using materials that reduce a building's energy use over time. The emphasis is on reducing the impact. It seems, is that the best we can hope for? Neri Oxman. This is not the best we can hope for. The reduction of carbon implies producing a lesser amount of it per building. The trouble with this approach is, first, that it is incremental. It doesn't get rid of the problem, and second, that it is agnostic relative to energy consumption categories. Not all carbon-based currency is consumed equally. The carbon footprint associated with food is different than the footprint associated with constructing or heating a home, and trading amongst them may only increase the problem. Since 2020, the anthropomass, the mass embodied in our built environment, has exceeded the biomass on our planet. What if all anthropomass could be transformed into biomass, and vice versa? If and when biomass can be utilized by the product and building industries, we will end the war against climate change for good. In doing so, we eliminate our impact and hopefully even reverse past damages. We will be consuming what we grow and growing what we consume. That is precisely the idea behind material ecology, to enable total synergy between the grown and the made by deploying digital fabrication technologies using natural bio-based materials for large-scale construction. The bones and muscles that make up our bodies are in constant flux. Bone remodeling is the process by which mature bone tissue is removed from our skeleton, and new bone tissue is formed throughout our lifetime and following injury. The same applies to extracellular muscles, where the remodeling of fibers enables damaged cells to be removed and replaced with new tissue. Consider these forms of remodeling and adaptation in product and architectural design. For example, materials with high dissociation rates and hydrophilic at Y can be specified by the architect for use in areas of the building where decomposition is desired to begin upon exposure to a certain level of rainfall. In contrast, lattices of mechanically robust materials can be used to reinforce the building where structural soundness is required. Environmental data and functional requirements would inform the computational design of buildings, whereby variables may be parametrically tuned to induce graceful program decay by design. This allows the predictable, responsible design of a structure and its interactions with its ecological niche across its entire lifespan, including even its afterlife. Through this project, we propose a way to temporarily divert organic materials from natural resource cycles, augment them with precise physical properties, and shape them into functional designs before enabling their program decay. Architect Carl Elefanti is known for coining the phrase, "The greenest building is the building that is already built." The reason is that the carbon emissions during construction are vast. Relative to the operating emissions of a given building, the embodied carbon of buildings is estimated to account for 11% of global carbon emissions and 75% of a building's emissions over its entire life cycle. But, again, if human-made mass qualifies as biomass and vice versa, the statement loses its meaning. The built environment of the future, the forest biome where you find multilayered and rich eco-niches composed of ground, herbs, shrubs, saplings, and trees all co-inhabiting a healthy and biodiverse environment. Consider now a similar range in the urban fabric with programmable tent structures to support the homeless, semi-programmable structures to support semi-permanent social functions, such as marketplaces, and towers that can stand the test of time. That is the kind of future I envision. It is somewhere between a pine tree and the Parthenon. We are foolish enough to bequeath the sixth extinction to our children and vain enough to question nothing. We are all responsible. The concrete forest is too much like a monoculture, and too little the thriving ecological niche it must become. The ability to digitally tune the mechanical, optical, and chemical properties of structures at nature's scale will enable architects to overcome the existing dimensional mismatch between physical matter and environmental forces. The material ecology approach offers methods and technologies for digital design and construction of variable property structures like variable optics glass, variable density concrete, and variable strength metals. Harnessing solar energy at urban scales by 3D printing optically transparent glass in the creation of architectural computers would be one such breakthrough. Another might be the application of variable density concrete 3D printing for the construction of lightweight and high-performance structures. NASA's acquisition of our digital construction platform for purposes of constructing buildings from moon regolith H indicates the relevance of our design approach. Robotic fabrication with bio-based materials will enable higher levels of customization and functionality in built structures that can be made to decay in a controlled and programmed manner.